to talk about standing waves. Standing waves are actually very important, and we'll see that as we go through the next couple of chapters. Okay, so if you have a string or a spring stretched between two fixed ends, well, not one fixed end, this is a fixed end, this end we can vibrate the string up and down. So we know that if we vibrate up and down once, we will send a wave in that direction. When it reaches the end, it will be reflected back. But if we vibrate up and down continuously, then we will be continuously sending waves over to that end. Okay, now if that end wasn't fixed, those waves would just keep going. But they're traveling waves. If that's a fixed end, what happens is if you continuously are sending waves, you're continuously disturbing the string, and effectively you will get that wave reflected back. Now what's happening at that stage is the reflected wave is traveling back. Okay, this wave is traveling, so you have a wave traveling that way, you have a wave traveling that way, and effectively at any split instant in time, if you froze time, then you would get the sum, the sum of the vibration or the displacement of the wave. So if you take this case here, just look at this wave first. Its displacement from its norm is that much. Now take the other wave. The other wave's displacement is exactly the same. So if you were to sum those two displacements together, you'd end up with an actual displacement of that much. And so that part of the string, whatever, will be displaced by that much. If you look at as time moves by, this wave will now move that way and this wave will move that way. So if you think about it, this wave will move that way, so it might have now moved so that it's like that. This wave will have moved that way, so this wave will probably now be like that. So now at this moment in time, the displacement of this wave is that much, the displacement of this wave is that much, so the overall displacement is now double. So that piece of the string will now be displaced by that much in total. You are adding the individual displacements. So as one wave goes that way and as the other goes that way, the displacement of the individual piece on the string is always the sum of the two displacements. And there will be areas where the sum of the two displacements, I'm not necessarily coinciding it like that, but there will all be areas where the sum of the two displacements might actually be zero. In a situation like this, if you have this displacement on one wave and this displacement on another, then you're going to get a displacement of zero. Okay? Similarly, you could have, that could be a wave, that's its displacement. You could have another wave coming backwards, and that will be its displacement. Again, the sum of the displacements is zero. Okay, so that means that piece of the string will not move in that situation. Okay, now what you find, and if you were to work out some very complicated maths in terms of where everything is at any instant in time, you find that you end up with what's called a standing wave. And the standing wave, so if this was a travelling wave, I have to do it like that. Right, that's the travelling wave, and then its reflected wave might be coming back. Okay, obviously the reflected wave will be of the same frequency and so on. Now it won't always do that because that is physically moving in that direction and that one is physically moving in that, so they aren't always overlapping by exactly that amount. But what you do find is that the sum of the two waves, when you add them together at any instant in time, what you get is you get a wave that is known as a standing wave, which is of higher amplitude than the wave, and we'll draw it like that because effectively what's actually happening is It's not that the wave is standing still, and it's not that you can have a particle in two places at the one time, but what's happening is this particular part of the string, effectively there's no string along here, this is just the line to show you, is vibrating up and down with maximum amplitude. This piece is vibrating up and down with that amplitude. This piece of the spring is going up and down with that amplitude, but there are areas of the spring, whichever you use, there are areas of it that actually never move, just by the nature of the summing of the two waves going in either direction. This piece will go up and down constantly. So if you were to look, what's actually happening at any time is there's this piece of the string, if you had the string straight, this particle of the string as such, or this bit of the string is going up and down like this. This bit of the string is going up and down like this. This bit of the string is going up and down like this and this. So it's not like it's there and there at the same time. It's just oscillating between those points. These points are known as the nodes. And the peaks are known as the antinodes. So these are nodes, places where the string actually stays still. These are antinodes. This is known as a standing wave or a stationary wave because effectively the wave doesn't appear to be travelling anymore. Even though it is the sum of a travelling wave going that way and a travelling wave going that way, the overall effect is to make the string or spring, the individual pieces of the spring vibrate like that. Okay? That's a standing wave. The important thing is that the frequency of the standing wave is exactly the same as the frequency of the vibration that caused it. Okay? And if you look, this length here is one wavelength. From here to here is one wavelength. So from that you can see that the distance between any two nodes is one wavelength divided by 2. Lambda over 2 is the distance between two nodes. Also, the distance between an antinode and a node is lambda over 4. So that's an important factor. So you need to know the definition of a standing wave. So that's in your book, along with a lot of other definitions such as coherent source, etc. And I have asked you to make sure you know them by Monday. So a stationary wave, the definition is when two periodic travelling waves of the same frequency and amplitude moving in opposite directions meet, they interfere with each other. The resulting wave that is formed is called a standing wave or a stationary wave. Okay? The frequency of the standing wave or stationary wave is the same as the frequency of the vibration that caused the wave in the first place, of the travelling wave. Okay, I think that's... Oh, and the only other thing I want to mention is polarization. And then I will do a video on the Doppler effect separately so that you can do the sums for homework that are in your book. Okay. Polarization very quickly. If I have, imagine a string, okay, from one end to another. So there's somebody here, there's somebody here, okay? If the person vibrates the string horizontally, that vibration will pass through to the person over here. If the person vibrates the string vertically, that's up and down, as opposed to this way, the string will pass to the other person. Now, let's put a slit. So effectively we have a wall now between the two people, okay? And we have a slit, and we're going to pass this into the slit and out the other side to the other person, okay? Now, if I vibrate the string up and down, then the vibration will pass through to the other person and they will see it, okay? However, if I vibrate the string horizontally, so in other words, this way, horizontally, then the slit will block the vibration and this person will see nothing. They will not experience that vibration, the wave will not pass through. That's what's known as polarizing a wave. It is allowing the wave through in a particular plane. light in particular is an interesting one because light is actually, when light is emitted from something, you get a wave in this direction, an electromagnetic wave. Remember when I say light, you also get a wave perpendicular to that. You also get a wave at every other angle. So effectively, light emits waves in every plane, okay? Every possible plane. If we pass that light through a vertical polarizer, all of the planes except the one that is vertical are blocked. So the person over here, if it was in terms of light, I'm showing you it like a string, but the same idea works with light. In terms of light, then the only thing that this person is going to see, the only light that they are going to see, is light that has been vertically polarized. Now, if we then, so they will still see light, but a lot of the light has been blocked. If we then apply another picket fence or whatever, a fence, okay, and this fence will horizontally polarize the light. Okay, so effectively you have light that can go through here now. That's the only light that's going to go through, all the other lights blocked. But if we then apply one that's perpendicular to that, that's going to block this light and no light will get through. Okay, because it's now horizontally blocked. So trying to put a vertical wave through a horizontal slit isn't going to work. So when you pass light through a vertical polarizer, and then you take a vertical polarizer and I suppose effectively you just turn it to right angles. Okay, so this is this way, effectively. This is horizontal, then no light can get through, or any other wave if you did the same thing. If you polarize it in one plane and then you polarize it in a different plane, then you will not allow any through. And the fact that light can be polarized means that it's a transverse wave, because only transverse waves can be polarized. If you were to think about this as just a vibration, if you were to think about this as a longitudinal wave, then the vibration occurs in this direction. So it will have no problem going through both the vertical or the horizontal polarizer. So longitudinal waves cannot be polarized. Since light can be polarized, and we can show that with polarizing sheets, light is a transverse wave.